Okay, so this is the second video covering AQA's energetics topic for A-level chemistry. And in this one, we're looking specifically at calorimetry. Now, calorimetry is all about measuring the enthalpy change of a reaction quantitatively. So I mentioned, I think in the first video, that one of the key differences between this topic in A-level chemistry and energy transfer that you did at GCSE is that bond energies aside, at GCSE you were only ever thinking about energy transfer in a qualitative sense. Either energy was transferred to the surroundings or from the surroundings. But this topic at A-level is quite calculation heavy. And so we're considering the methods or the experimental and practical methods that we would use and also the data that we would get from those experimental and practical methods as a way of then actually calculating the enthalpy change for a particular reaction. Now, given that it's all about calculations, there are a couple of equations that we have to know and understand, and that's what we're going to turn to next. So here's the first one, the first equation. So this is focused on calculating or working out the energy transferred in a particular practical or experiment that we do. Now, it relies on the relationship between the change in temperature of a substance, the specific heat capacity of the substance, and the mass of that substance. Now, nearly everything that we're going to be doing, what we're going to be measuring the change in temperature of is either going to be a solution or water. So when we're looking at the mass, what we're actually looking at is the mass of the solution or water. So just to remind you what we might mean by solution, we could be talking about copper sulfate solution. So we're going to be measuring the temperature of the water or the solution, and then we're going to be using the specific heat capacity as well to work out how much energy must have transferred to result in that temperature change. Now, even though we might be using a solution like copper sulfate, the specific heat capacity that we're given is nearly always water. In fact, I can only ever think of it being water, but I just want to have the nearly just in case. So there is an assumption there. So even if we might be using copper sulfate, we're essentially assuming that it's water. Now that's sort of understandable because what we're actually measuring the temperature of is the immediate surroundings of the reaction, and that reaction is taking place in an aqueous environment. So really what we are mostly measuring the temperature of is of the water in that solution. Just thinking about the units, obviously if we're talking about energy, then that has to be joules. If we're talking about mass at chemistry, that's grams. If we're talking about temperature change, that's Kelvin. And if we're talking about specific heat capacity, well, like I say, you'll get given the values and you'd get given the units, but just so you're aware of them, it's joules per gram per Kelvin. Now, regarding the change in temperature, sometimes you're given the data. So you're given the temperature rise or temperature change. And it could be given to you in degrees Celsius. But then one of the important things to remember or to realize is that a change in temperature in degrees Celsius is exactly the same as a change in temperature in degrees Kelvin. So if the temperature rose by 10 degrees Celsius, that is a temperature rise of 10 Kelvin. So as a unit, 1 degree Celsius is the same as 1 Kelvin. So there's no conversion needing to happen here. There's no converting of Celsius into Kelvin. The other thing just to point out is that what we're fundamentally working out is the energy transferred in whatever reaction or practical that we do. So for example, we maybe add 5 grams of zinc to 50 centimeters cubed of 1.0 mole per decimeter cubed copper sulfate solution, and the temperature rise that we'll be measuring is of that 50 centimeters cubed of solution. So we are working out the energy transferred for that specific and particular practical that we're doing. But if you remember, what we're really fundamentally looking at in this topic is enthalpy change. And going right back to the beginning, one of the things that we said in the first video is that the units of enthalpy change are kilojoules per mole. So that's why this is equation 1. This gets us the energy transferred in the particular practical that we're looking at or considering, but what we then need to do is to turn that into an energy transfer per mole. So that's where the second equation comes in. So this follows on from the first, and once we look at some examples of actual calculations shortly, I think hopefully it'll all come together. But now you can finally see that we've got delta H, we've got the enthalpy change. We've got Q from the previous equation, so that's the Q that we've measured. But the Q that we measured was in joules, but of course enthalpy changes in kilojoules per mole. So one of the things that we have to do is we need to convert Q into kilojoules, and so that's why we've got the divided by 1,000. You could do the dividing by 1,000 straight at the end of equation 1, but I've just put it here just to sort of emphasize the point that Q needs to be converted into kilojoules. And then the other thing is this will be the moles of the limiting reactant. So in many practicals, typically one of the reagents will be in excess, and that will be particularly the case here. So this is to ensure that the reaction goes to completion with at least one of the reagents. And so quite often one of the early parts of the question, or one of the parts of the question, might well be to find out which of the reagents is the limiting reactant. And then what you've got to remember is the moles that you're using here to work out the enthalpy change is going to be based on the moles of the limiting reactant. Finally, the one last thing I haven't spoken about in this equation is the plus and minus at the beginning. Now, they are the signs that we're going to give in our final answer to make it clear that the energy transfer is endothermic or it's exothermic. So remember, exothermic is a negative change in enthalpy and endothermic is a positive change in enthalpy. Now, I'm afraid the maths itself doesn't give you the correct sign, so this is a decision that you have to make at the end. So one of the things that I suggest is that whenever you write this equation out, when you first start putting the values in, that you include a plus and a minus. And the reason to do that is to sort of remind you, to prompt you to think about that at the end so that you choose the correct sign for your final answer. Now, the way that you choose the correct sign is to look back at the original temperature change data. If it said that the temperature change was an increase, that there was a temperature rise, then that means it must have been an exothermic reaction, so you would put a minus in front of it. If it tells you that there was a decrease in temperature or a drop in temperature, then it's going to be endothermic, so you're going to put a plus. Now, you don't have to put the plus, but I would say that if you always force yourself to put a sign in front of the final value, then that forces you to double check, was the reaction endothermic, was the reaction exothermic? So many students will do the whole calculation, will get the final value correct, and then they will forget to put, say, minus, because they'll forget to look back and recognize that it was an exothermic reaction, and they lose marks. And these are easy marks too. So, to help you avoid making that mistake, when you first write the delta H equation, when you're doing a calculation, I suggest you put the plus and the minus there to force you to make a decision, to force you to look back and make a choice. So what we're going to do now is we're just going to look at one of the practical methods for determining an enthalpy change in a reaction. And we'll look at how that practical gives us the information that we need for both of these equations. So this is a sort of outline of the apparatus that we might use to work out the enthalpy of combustion for a particular substance. So in this particular drawing example, we are doing it for methanol. So there's methanol there. A few things to just mention. Notice we've got a copper can that the water is in, so we are measuring the temperature change of the water. You can see the thermometer is in the water. The fact it's copper is really to allow the energy to be transferred efficiently and quickly from essentially where the reaction is taking place into the water, so that the water warms up. We've got these heat shields really because if you've ever had a flame and you've walked past a flame, you know that they can flicker and it can waver, and so our flame might go this way or that way. So it's really to try and ensure that the reaction is focused, as it were, on the copper can and therefore into the water. Another important thing to just point out is that the thermometer does not or should not touch the base of the copper can, because otherwise what we'd be measuring the temperature of then as much as anything would be the copper can rather than the water. So that's something to bear in mind. And whilst it's not shown in this diagram, because it would be tricky to do so, what you would try and do throughout the practical is stir the water to ensure that there's a sort of an even distribution of temperature throughout, so that you are measuring a sort of an accurate temperature of all of the water. Now, if we just focus back on the fact that this particular diagram is on methanol, so let's just at least write what it is, what enthalpy change it is we're working out. And so we're doing the enthalpy change of combustion. So if we think about the equation for that, we are combusting 1 mole of methanol, so that's CH3OH. That would be a liquid, because obviously that's sort of what we can tell from the diagram here. It's going to combust completely with oxygen, so we're just going to put the O2 gas. And then if we think about what products that's going to form, it's going to form carbon dioxide, which is a gas, and it's going to form water, which under standard conditions is a liquid. And now we just need to balance everything. So we start with the carbon. So we've got 1 carbon on the left and 1 on the right, so that's fine. Then go to the hydrogens. We've got 4 on the left and currently only 2 on the right. So we're going to put 2 in front of our H2O. And then lastly, we look at the oxygens and see, and it's very important here actually to remember, this is where people get caught out quite a lot, that we have an oxygen in our methanol. So currently we have 3 on the left and we have 4 on the right. Now we cannot change this, we cannot put a coefficient in front of this methanol formula, because the whole definition of enthalpy of combustion is the combustion of 1 mole of a substance, so that has to remain as 1 mole. So to get an extra oxygen atom, so that it's 4 on the left to equal the 4 on the right, it's going to be 3/2 in front of the oxygen there. So let's remind ourselves of the 2 equations that we're using to work out enthalpy change. Okay, so the thermometer is going to provide us with the final temperature, and it's going to provide us with the initial temperature. And if we subtract the initial from the final, what we get is the temperature change. So the thermometer is giving us the temperature change in the reaction. So it's giving us delta T. The water, we would measure the volume. So the volume of the water, and that can be in centimeters cubed or milliliters. They are both the same unit of measure. That equals the mass in grams. So for example, if we had 100 centimeters cubed, that equals 100 grams. So that's given us the mass. It also would give us the specific heat capacity, and that's because the substance that's actually changing temperature is the water. So now we've got MC and delta T for the Q equals MC delta T. So the thermometer and the water are giving us the data that we need for that first equation. And then for the second equation, the second piece of information that we need is the number of moles of methanol that combusted. So if we measured the mass of the burner and the fuel before the experiment took place, before any combustion, and then once we'd sort of capped it and we'd finished measuring the temperature change, we then took the final mass of the burner and the fuel, then the difference between those 2 masses will be the mass of the methanol that combusted. So if we then have mass, we could work out what the MR of methanol is. So we can work out the number of moles that caused that energy transfer by dividing the mass of the methanol that combusted by its MR. So let's see an example. So here, the first piece of information they're telling us is that in an experiment, 0.600 grams of propane was completely burned in air. So they are straight away just giving us the mass of the fuel that was completely burned or combusted. Then they tell us that heat evolved raised the temperature of 100 grams of water by 64.9 degrees Celsius. So they've very kindly given us the mass of water, so we haven't had to be confused or thrown by them giving us a volume. They've given us the temperature change without us having to work out the temperature change from an initial and final temperature. And then they are asking us to calculate the enthalpy of combustion of propane, which we know is when a mole of propane is completely combusted. And they are then finally giving us the specific heat capacity of water. So let's look at our equation, our first equation, which is Q equals MC delta T. Okay, so we just need to plug in the numbers now. So we know that the mass of the water is 100 grams. We know that the specific heat capacity is 4.18, and we know that the change in temperature is 64.9 Kelvin. So using our calculator, that gives us a value of 27,128.2 joules, and we'll do the conversion into kilojoules now. I think it's the best time to do it. So that equals 27, we're dividing by 1,000, 0.13 kilojoules. Okay, so our energy transferred in this particular experiment is 27.13 kilojoules. So now let's look at our second equation. So delta H, so the enthalpy change, and then I'm going to put the plus and minus because I'm going to think about that at the end. And I've already turned Q into kilojoules, so I'm just going to write that value, 27.13, and then it's going to be divided by the moles. So one of the things that we need to do is work out how many moles of propane were actually combusted. So they've given us the formula, so it's C3H8, and they've given us the mass, and we know that moles equals mass divided by MR. So we work out the MR of propane. So we've got 3 carbons, so that's 36, 8 hydrogens, that's 44. So our moles is going to be 0.600 divided by our MR, which is 44, which equals 0.0136. So I put that into our second equation. And then, of course, what you always try and do is keep the numbers in your calculator. So even though I'm doing rounding when I'm writing it down, you try to keep the numbers in your calculator as much as you can, and then do the rounding right at the very end. Okay, so let's make a decision about the sign before I actually put that calculation into my calculator. And they told us it was a temperature rise. Okay, so the heat evolved to raise the temperature. So that tells us it's exothermic. So we have to remember now to put a minus value in front of our final answer. So I now do the calculation and I get an answer of 1,989.4 kilojoules per mole. But we should get into the habit of giving our final answer to the correct number of significant figures. And if we look at the data we've been given, the mass was to 3 significant figures. The temperature is to 3 significant figures, or the temperature change. The specific heat capacity is to 3 significant figures, and there is a little bit of ambiguity regarding the mass because 100 grams could be 1, 2, or 3 significant figures. But I think based on the data we've been given, we have to assume that it's 3 significant figures also. So that gives us a final answer of minus 1,990 kilojoules per mole. Now, after doing a calculation like that, a classic question or classic exam question is, why is the value that you've calculated less than the data book value? So if we're talking about combustion, then we've got to remember the definition. The definition is that the change in enthalpy when 1 mole of a substance is completely burnt in oxygen under standard conditions. And that's the completely burnt in oxygen is our caveat there. Because any practical that you do, no matter how well ventilated the room, there is always a degree of incomplete combustion, and that incomplete combustion has a significant impact on the energy released. So and then you've got to be very clear about this, if the question is about combustion, right, and it asks you why is it less than the data book value, then your answer is there is a degree of incomplete combustion. Okay, and so your calculated value will always be less than the data book value. So it's not just saying it's different, it's saying it's less. So less energy is released when it's a combustion reaction because there will always be a degree of incomplete combustion, and the data book value is based on complete combustion. So that's how we would determine the enthalpy of combustion, but the specification points out that you could be asked to work out the enthalpy change for a reaction, for various reactions by calorimetry, and then the examples that they list include dissolution or the dissolving of potassium chloride, the dissolving of sodium carbonate, a neutralization reaction, say with sodium hydroxide and hydrochloric acid, a displacement reaction between copper sulfate and zinc, and like the one we've just seen, or the one that we saw the experimental setup of the combustion of alcohols. Now, it doesn't matter which of those we use, we'll always be using Q equals mcΔT and delta H equals plus or minus Q in kilojoules divided by moles. So we'll be using both those equations, whichever type of reaction. So the fundamentals stay the same. There are just tiny differences, though, regarding the actual experimental technique, but we'd still be doing the same fundamental measurements. So anyway, let's have a look at another calculation example, and this time with a different type of reaction. So to start with, I suggest you maybe pause the video and just read through the information that's given, so that when I begin to talk it through, you're already familiar with what it is that it's described. So pause the video and read through the information that the question's giving you. Okay, so I think the first thing to notice or to pay attention to is the line that says work out which reagent was in excess. So a habit of mine is for when there's a reaction equation is to write the molar ratios above the reaction equation, just so that they stand out a bit more clearly to me. So first of all, I'm going to work out the number of moles of silver nitrate that were added. So we've got 50 centimeters cubed of 0.10 moles per decimeter cubed. So we're going to multiply the volume, which needs to be in decimeters cubed. So we're going to divide the 50 centimeters cubed by 1,000 times the concentration, which is 0.10. And that equals 5.0 times 10 to the minus 3 moles. Next, we're going to work out the number of moles of zinc. So that's mass divided by MR, which is 0.2 divided by 65.4, which is 3.0 times 10 to the minus 3. Now the molar ratio, according to the equation, should be 2 to 1. And we can see that we don't have double the moles of silver nitrates compared with zinc, so our limiting reactant is the silver nitrate, and the reagent in excess was the zinc. And now we're ready to use the two equations that we've learned about regarding calorimetry. So the first one is Q equals mcΔT. So regarding the mass, we're actually looking at the volume of solution. So we've got 50 centimeters cubed, so that means we're going to have 50 grams as our mass. The specific heat capacity they give us as 4.18 joules per gram per Kelvin. And then finally, the change in temperature was a temperature rise. So they've given us the actual change in temperature of 4.3 degrees. So we put those into our calculation, and that equals 898.7 joules. And we'll do the conversion to kilojoules straight away. So 0.8987 kilojoules. So where people often get caught out at this point is the mass. Because when they read back through the description, they see a volume, and that doesn't leap out at them, but they do see a mass of zinc powder, and so the moment they see it's 0.2 grams, they start to think, well, that's a mass, that's what I need to put into my calculation. But you've got to remember that the mass refers to the substance that's changing temperature, so it's going to be related to the specific heat capacity, and they give us the specific heat capacity of the solution, and they make it clear it's of the solution. So obviously the mass has to refer to the solution, and as I said earlier, mass is always going to be of the solution or of water, so really you need to be looking at volumes, and then there's a slight assumption that the density of any of these solutions is going to be the same as water, but we're converting our 50 centimeters cubed into 50 grams. Okay, so just before we just do the next bit, which is going to be delta H, the actual enthalpy change calculation, let's just pay attention to the fact that in the question it says then calculate the enthalpy change for the reaction, and then it says per mole of zinc that reacts. So we're just going to be really careful here. So it says per mole of zinc that reacts. So the number of moles of zinc that reacts is going to be half the number of moles of our limiting reagent of silver nitrate. So we used 5.0 times 10 to the minus 3 moles of silver nitrate. That was our limiting reagent. We've got a 2 to 1 ratio, so that means the number of moles of zinc that actually takes part in this reaction is half of 5 times 10 to the minus 3, which is 2.5 times 10 to the minus 3. So the moles that we'll be going to be using in our next equation is going to be the moles of zinc that actually reacts, because the question asks us per mole of zinc that reacts. And so that's going to be half the number of moles of silver nitrate because of the molar ratios, 2 to 1. So that's going to be 2.5 times 10 to the minus 3. So let's write our second equation out. So it's plus or minus because we're going to make the decision about whether it's an exothermic or endothermic reaction in a second. We've got the energy transfer, but in kilojoules divided by the moles, but this reaction is asking us per mole of zinc, so it's going to be the number of moles of zinc that took part in this reaction. So our calculation is minus because the information that we're given, it says that there's a temperature rise, so we know it's exothermic, so we put the minus sign. Our energy transfer in kilojoules is 0.8987, and then divided by our number of moles of zinc, which is 2.5 times 10 to the minus 3, and that gives us a final answer of minus 359 kilojoules per mole. Now, I've written the answer to three significant figures, although when we look at the information that's given to us, actually, I don't think this is a great question in that respect, because we've actually got the mass of zinc powder to just one significant figure, which is not something that would happen in a real exam question. What I would say is that typically, probably about 90% of questions, the correct number of significant figures in an actual AQA test question is 3, excepting certain topics where there are certain other requirements. There are occasionally 2 significant figure answers, so you do need to not just automatically do 3, but if in doubt, do 3. But always try and check the information that you're given, and basically your number of significant figures is limited by the fewest number of significant figures in the data you've used. So you cannot have an answer that is more precise, and that's what we mean by having more significant figures. You cannot have an answer that's more precise than the information you were given to calculate it. So the question that we just did, the actual calculation, the approach, is basically a similar one behind the actual core practical in this topic, energetics. So you remember that the spec listed a variety of reactions that you could be asked to work out the enthalpy change for, and when it comes to core practical 2, those sorts of reactions are the reactions that could feature in the core practical. So we're going to consider one in particular, but the principles behind this are the same with the others. And it was listed in the spec as a displacement reaction between copper sulfate and zinc. One thing we should say is that displacement, that use of the word displacement, is a bit of a misnomer, because really it's a redox reaction. There is no swapping of partners as such, because the sulfate ion is completely separate, it's completely independent, it's a spectator ion. So really we've got the oxidation of zinc and the reduction of copper taking place in this reaction. Now the apparatus is a little bit different to what it was for the combustion reaction, but the general principles still apply. So at the heart of the apparatus is a polystyrene cup. But otherwise, the principles that we're following are identical to before. We've got a thermometer in our solution, and so that's going to allow us to measure delta T. Our solution, the volume of our solution is going to give us our mass. One of the assumptions is that the specific heat capacity of these solutions are the same as water, so we have C. So we have the information to work out delta T from the thermometer. We have the information to work out the mass from the volume of the solution, and we know specific heat capacity of the solution is assumed to be the same as water. The only other thing that we need to do is we would need to work out what the limiting reagent was, so that when we did the delta H calculation, we used the correct number of moles. But you've seen from the calculation that we did just a little bit earlier, the example question that we did a little bit earlier, the sorts of things that you need to look for regarding that. Now, I just want to use this diagram to explain what we really mean by surroundings. So if you think about it, the actual reaction is between zinc and copper ions. So zinc solid and copper ions. And so this is taking place in an aqueous environment. The copper sulfate is aqueous. But that means that the water really is the surroundings. And so what we're really measuring the temperature of when we use our thermometer are the immediate surroundings of the reaction. Okay, so that's quite important. And the polystyrene cup is to reduce heat loss to the external surroundings, if you like. So we're trying to ensure that as much of the energy that's released is contained within the water, so that we're getting as accurate as possible a measure of the energy transfer through the change in temperature. Now, being a core practical, one of the things that you do have to understand and appreciate and be familiar with is the method. But equally, like a lot of the core practicals in A-level chemistry, it isn't just about being aware of the method, but it's about being aware of how you use the data that the practical gives you, how you then analyze the results. So a key feature in this core practical is the analysis of the results that you get from doing the practical. So first of all, you would pour in your solution, and you would start a stopwatch, and you would measure the temperature of that solution every minute, and you would do it probably up to 4 minutes. And then at the 4th minute, you would add the other reactant. So in this case, we're adding zinc. And then every minute, you're going to continue to record the temperature for maybe up to 15 minutes. So the only time that you don't have a temperature reading is when you added the zinc, the 4th minute. So you've got a temperature reading at 0, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 minutes, and so on. You then plot a temperature versus time graph. And just to be clear, when you're talking about a graph and you say something versus something, you're always giving the y-axis first and the x-axis second. So we are plotting our results on a temperature versus time graph, and then we're going to get, as you'll see in 2 examples in a minute, we're going to be able to draw 2 lines of best fit, basically a line of best fit for the temperature leading up to us adding the second reactant, and then a line of best fit after we've added the second reactant. And then we extrapolate the lines back to the 4th minute, and then we then measure the difference between those 2 lines at the 4th minute. That was the moment we added the second reactant, and this is going to be our delta T value. This is going to be our change in temperature. So on the left, we've got an example graph for an exothermic reaction. That's because there's a temperature rise. And then on the right-hand side, we've got a graph that illustrates what it might look like if it was an endothermic reaction. So if I talk through the graph, the exothermic graph first. So we added our first reagent, which would be the solution. And we measured the temperature of the solution every minute from 0 minutes. And then at the 4th minute, we added our second reagent. And then from the 5th minute, we started measuring the temperatures again. And we keep doing that maybe up to 15 minutes. But what we've got to see is we've got to certainly see that the temperature is decreasing after the reaction if it's an exothermic one. Then we draw our lines of best fit, and we're looking at the data before the reaction took place and the data after the reaction took place separately. So we draw a line of best fit for our temperature of the solution at the beginning. So that really probably should be a horizontal straight flat line like that. And then we look at the data after the reaction took place. And what we focus on, in terms of an exothermic reaction, we focus on what would now look like a cooling curve. So these data points here are the cooling curve points. And we extrapolate, we draw a line of best fit through that cooling curve points, and we extrapolate back to the 4th minute. So both of the lines of best fit are extrapolated to the 4th minute, and then we measure the difference between those 2 lines of best fit, and that gives us delta T. But just to be clear, we ignore the data point where the temperature is still rising. So we're focusing only on the cooling curve data points when we look at exothermic. In endothermic, it's exactly the same, only this time we're focusing on a warming curve. So when we do our line of best fit for using the data after the reaction's taken place, we are drawing a line of best fit through the warming curve points, and we are extrapolating back to the 4th minute with that line of best fit. And again, it's the difference between the 2 lines of best fit that gives us delta T. Now, exam questions have featured quite heavily on this core practical, and they can ask you to describe the method or the way that you would how you would arrive at the results that you needed to do the calculation, and that would include talking about measuring the temperature every minute, adding the second reactant at the 4th minute, recording the temperature for a further 10 or so minutes, and then you would also need to talk about plotting a graph of temperature versus time. You would have to talk about drawing 2 lines of best fit. You would have to talk about extrapolating them back to the 4th minute, and you would have to talk about measuring the difference between those 2 lines at the 4th minute and getting delta T. So you would have to explain all of that in your method, in any method question regarding this core practical. Equally, they could give you the data values and they could ask you to then plot the graph and then to work out delta t. And so what you would have to remember in that type of question is that once you plotted the graphs, that you drew you drew the line of best fit, the lines of best fit, and then you measured the difference between those two lines. So you would be getting assessed for drawing the correct lines of best fit and then for doing the correct delta t. Then they might then ask you to do a calculation question based on that delta t. If, of course, you'd got delta t wrong, if you'd made a mistake with the graph, they wouldn't carry that error forward, so you would be marked afresh when you did the actual calculation. And then just remember, when it comes to the calculation, determine which of the reagents was the limiting reagent, and you base the number of moles in your delta H part of the calculation on the limiting reagent. Now, with the combustion reactions earlier, we saw that we could get a classic exam question where it asks us why the value we've calculated is less than the data book value. For combustion reactions, it was because of incomplete combustion. That is not relevant here, but what we have got is we've still got heat loss to the surroundings. So despite our best efforts, not all the energy released stayed in the polystyrene cup, so we weren't measuring all of the energy released. So if they haven't used the lid and they ask you for how might you make your answer more accurate, then you could use a lid. That would be one thing absolutely to do. But essentially, if you have a non-combustion reaction and you're asked why the value you've calculated is less than the data book value, it will be because of heat loss to the surroundings. That will be the answer. So that concludes the calorimetry side of the topic. So that's the second part of 4 regarding energetics. If you have any questions, please just let me know and I'll do my best to answer them.